When two supermassive black holes merge, they generate a gravitational disturbance so violent it physically distorts the surrounding geometry of the universe. This image of the black hole M87 star shows a structure governed by classical general relativity. The dark central void is bound by the event horizon, a mathematical threshold where the escape velocity exceeds the speed of light. General relativity predicts that the matter falling past this horizon is crushed down into a gravitational singularity at the very center. This is a point of zero volume, where the entire mass of the black hole is concentrated at infinite density. Quantum mechanics operates on an opposing rule. The state of a physical system at one point in time must mathematically determine its state at any other time. Quantum information must be perfectly conserved. A zero-volume singularity extinguishes all physical and quantum structure of infalling matter. It creates a mathematical void where the history of a particle ceases to exist. Theoretical physicists first formalized this incompatibility as the black hole information paradox. It highlights a direct contradiction between our laws of macroscopic gravity and our laws of subatomic particles. Stephen Hawking's calculations showed that quantum effects near the horizon cause black holes to emit low-energy thermal radiation. As a black hole radiates, it slowly evaporates over billions of years, shrinking away completely without returning the quantum information it trapped. This absolute loss is supported by the classical no-hair theorem, which dictates that a black hole projects no internal structural data to the outside universe, leaving behind only three measurable properties: mass, angular momentum, and electric charge. If classical singularities dictate reality, the conservation laws of physics fail entirely. To maintain the structural integrity of quantum mechanics, the interior of a black hole cannot be an empty vacuum. A subset of superstring theory, known as Type 2b, offers a mathematical resolution that replaces the singularity with a physical object. String theory replaces zero-dimensional point particles with one-dimensional strings. The fundamental constituents of matter and forces are double-ended or looped bundles of energy, vibrating in complex frequencies. Under this framework, a black hole is a fuzzball. It is a sphere of highly compressed strings, representing the ultimate, terminal phase of degenerate matter. The event horizon is no longer an empty mathematical boundary. It is a dense, vibrating mesh of interwoven strings. Calculations by physicist Samir Mathur proved that the physical radius of this string ball matches the Schwarzschild radius perfectly. The solid surface of the fuzzball rests exactly where the classical event horizon begins. When matter falls onto a fuzzball, it does not vanish into a central point. The incoming strings fuse directly with the surface, adding their quantum information to the larger, entangled composition of the object. Because this surface has physical structure, its quantum data slowly tunnels outward. It imprints delicate correlations onto the outgoing Hawking radiation, carrying the exact history of the absorbed matter back into regular space. To empirically confirm this framework, we need a method for measuring the physical, structural properties of an event horizon from Earth. To measure an event horizon, we have to look at the macroscopic geometry of spacetime. In general relativity, freely falling objects travel along paths known as geodesics. Curvature in space is defined by the failure of parallel transport. If two particles begin on parallel paths, but are forced to converge or diverge without any physical force acting upon them, the space they are traveling through is curved. This diagram shows how curvature is quantified. An incoming gravitational wave, vector k, intersects two adjacent geodesic paths, A and B. The vector connecting A to B defines their exact spatial separation over time. By taking the second derivative of this separation vector, physicists calculate the relative acceleration between the two freely falling particles. This calculation is known as the geodesic deviation equation. The crucial component of this equation is the Riemann tensor. This mathematical object contains the first and second order derivatives of the spacetime metric, and it is the exact value that dictates curvature. Physically, a non-zero Riemann tensor manifests as tidal forces. It determines how objects are stretched or compressed as they move through a gravitational field. Physicists apply this equation to linearized spacetime, isolating slight metric perturbations against a flat background space to analyze incoming gravitational waves. Spacetime curvature is an active physical deformation, strictly defined by how adjacent freely falling particles are forced to accelerate relative to one another. To identify pure wave-like solutions in the Einstein field equations, physicists must strip away the ambiguities inherent to shifting coordinate systems. They apply a specific mathematical constraint called the transverse traceless, or TT, gauge. This process isolates the two true dynamic degrees of freedom in general relativity. The TT gauge yields a direct result. A traveling gravitational wave is mathematically equivalent to an oscillating Riemann tensor. Because these waves are transverse, they produce physical deformations exclusively in the plane orthogonal to their direction of propagation. If a wave hits a circular ring of test particles, it forces them into specific geometric oscillations. This diagram illustrates the linear polarizations of a gravitational wave. The plus mode stretches the ring vertically while compressing it horizontally, mapping particles to the solid ellipse. The cross mode operates on the exact same mechanics but rotates the deformation axis by 45 degrees. This subsequent diagram displays how these two linear degrees of freedom combine to create circular polarizations, rotating the axis of the ellipse either clockwise or counterclockwise over a single period. These specific cyclic deformations dictate the exact physical movements we must monitor to intercept metric perturbations reaching Earth. In the TT gauge, a gravitational wave is an oscillating Riemann tensor writing its geometric data across physical space. We can scale this geometric framework from a microscopic ring of test particles up to macroscopic astronomical bodies colliding in deep space. When two massive fuzzballs merge, their string-based surfaces physically impact, intertwining their constituent loops and releasing kinetic energy. The volume of a fuzzball scales directly with the Schwarzschild radius, resulting in a mass density inverse square rule. As fuzzballs combine and increase in mass, their mean density actively decreases. This decrease is driven by fractional tension. When strings collide, they do not simply pack tightly together. Instead, they fuse to become larger, more complex strings with additional vibration modes. This fusion process causes the tension of the strings to exponentially drop. They relax and extend to considerable lengths, ensuring the core never compresses into infinite density. A classical black hole merger is the collision of two empty mathematical boundaries containing zero internal structure. A fuzzball merger involves the violent physical collision of degenerate matter. The complex geometry of the fusing surface generates unique, non-trivial vibrational modes as the object settles into its new mass. Because fuzzballs are physical, extended objects, their collision rings the fabric of spacetime, producing mechanical vibrations that differ strictly from those of an empty vacuum. Earth-based gravitational wave observatories, like LIGO and Virgo, are built to detect these specific mechanical vibrations. Their massive perpendicular vacuum tubes act as an isolated orthogonal ring of test particles, directly measuring the geodesic deviation caused by an incoming wave. After the peak intensity of a merger, the resulting single body continues to vibrate, emitting a fading gravitational wave signal known as a ringdown. Classical GR predicts a singularity's smooth ringdown decays rapidly to a flat line. Fuzzball merger simulations, however, show a waveform decaying noticeably slower due to string tension. As vibrations fade, secondary echoes appear, physically reflecting the string surface within the gravitational wave's amplitude. By accurately measuring the metric perturbations of geodesic deviation, observatories have the capacity to detect these exact echoes. Identifying this signature in the data would prove black holes have physical surfaces, resolving the information paradox and providing the first empirical evidence for string theory.